Next, we'll analyze the global dependence of the optimal objective value of a linear program on the right-hand side of the constraints. So let's consider an LP in the standard form. We have minimize C transposed X subject to AX is equal to B and X is greater than or equal to 0. So we assume that A is a matrix that has full row rank, meaning that the rows of this matrix are linearly independent, and assume that we can actually vary the right-hand side of this constraint, and our goal here is to see how this will impact the optimal objective value when we make any changes to the right-hand sides. Alright, so let's denote by x of b the feasible region for this LP as a function of the right-hand side. So it's gonna be all x's such that ax is equal to b, x is greater than or equal to 0. So essentially the feasible region for this LP, right? But assume that again it is a function of b, so meaning that we can vary the right-hand sides here, and depending on how we change b, our set x of b will change as well. We are interested in the situation when our LP is feasible, so let's denote by f the set of b's for which our problem is feasible. So meaning that x of b is not empty. And then what is x of b? This is the set of x's such that ax is equal to b. And we want to have feasible b, so it means that there must be x's such that ax is equal to b. So essentially this is the set of all the b's given by ax where x is greater than or equal to 0. Alright, so these are defined by linear equations, and obviously this set F is a convex set. And what we are interested in is to see how the optimal objective value z depends on the right-hand side b. So we are going to define our objective function value z as a function of b that will take an argument in this set f. So we are going to consider the b's for which the feasible region of our LP is non-empty, and it's going to be from f to r, because the objective function z takes a real value. So then our z of b is defined as follows. So it's equal to the minimum of C transposed X such that X belongs to our feasible set X of B. So this is a function of B, of course, right? So, and we want to figure out what shape this function has. We already saw that the domain of our function is a convex set, and what we are going to show that z of b is in fact a piecewise linear convex function. And for this we are going to use the dual LP. So the dual LP is given by maximizing b transposed y. Here we have the equality constraint, meaning that the dual variables will be unrestricted in sign, and because x is non-negative, we will have the dual constraints of less than or equal to type. So you have maximized b transposed y subject to a transposed y is less than or equal to c. So this is our dual problem, and we'll also assume that the dual problem does have a feasible solution as well. So if we denote the feasible region for the dual by y, which is the set of y's such that a transposed y is less than or equal to c, then we assume that this set is non-empty, meaning that we have a lower bound on the optimal objective value for the primal, right? Because as soon as we have a feasible solution for the dual, it gives us a lower bound on the primal. And by duality theorem, this implies that both primal and dual problems have an optimal solution. and the optimal objective values for both match. Now let's consider the optimal basis for the primal LP, and let me write down the corresponding dictionary. So we have Z is given by CB transposed B inverse times B, so this is our optimal objective value. Then plus the reduced cost is Cn minus CB transposed B inverse times n, and this is multiplied by xn, the vector for the non-basic variables. And then for the constraints, we have the basic variables expressed through the non-basic variables. So xb is given by B inverse times B, and then minus B inverse times n xn. Let's see what happens to the optimal objective value Z when we vary the right hand side B. So first of all, if we have a degenerate basis, meaning that some of the entries of this vector B inverse times B are equal to 0, then a slight variation of B may result in infeasibility. So for now, assume that we have a non-degenerate basis, meaning that this is strictly greater than 0. Now, if this is strictly greater than 0, because this right-hand side here is a continuous function of B, a slight variation in B will preserve the sign of this expression here, so it will still be greater than 0. Also, when we change B small, this part here is not affected, meaning that the optimality condition is still satisfied, right? So a slight variation in B small preserves optimality and feasibility, and also the expression in the objective here CB transposed B inverse actually gives us the optimal value for the dual variable. So let's denote this by Y star transposed. So then our Z of B is going to be given by Y transposed, actually Y star transposed, right? So the optimal dual solution multiplied by the vector B. All right, and we can see that this dependence is linear, but of course keep in mind that we are talking about the local dependence here. So we assume again that the basis is non-degenerate, so meaning this is strictly greater than 0, and in this local neighborhood of the current B value we have this dependence. So Z of B is locally linear, right? Also, because the matrix A is of full row rank, and also the dual problem is assumed to be feasible, this implies that the dual feasible region has at least one extreme point, meaning that the optimal objective for the dual can be expressed as the maximum of Y bar I transposed multiplied by B for I between 1 and n, where this yi bar for I between 1 and n are assumed to be the extreme points of Y capital. This is the case because, as we know, in order to find the optimal solution for our dual problem, we just need to pick the best extreme point, right? So essentially we can just enumerate all the extreme points and then just pick the extreme point with the highest objective value, right? So as a result, what we see here is that this function Z of B is locally linear for every B small, such that this basis here is non-degenerate, meaning that B inverse times B is strictly greater than 0. In particular, the fact that we have a non-degenerate basis here implies that if we look at row 0 of the optimal dual tableau, all the non-basic variable coefficients will be non-zero, meaning that the dual problem will have a unique optimum. So that's why the maximum here is going to be unique, and as a result we have this locally linear dependence. But now what happens if some of the entries here are equal to 0 and we have a degenerate basis? So in this case there is a possibility of alternative optima for the dual problem, And as a result, there may be a couple of different extreme points where this maximum is achieved for a particular b value. So in this case, we don't have the local linearity anymore, but we still have a very special structure for this z of b function. In particular, we have the pointwise maximum of linear functions here, because look, for every fixed yi bar, this is a linear function of b, right? So, and here we have a pointwise maximum of linear functions essentially. So let's illustrate what type of structure these functions have geometrically. And first, let's discuss a more general setting where generally you have convex functions f1, f2, and so on, fk. And we consider the pointwise maximum of this set of convex functions. And of course, the linear case is a special case of this situation because linear functions are convex. So, but for a pointwise maximum of convex functions, we can easily show that this function f of x will also be a convex function. And in particular, for the linear case, we have the piecewise linear convex function. So, and this is how it looks like geometrically. So let's say if we had a function of one variable, we have a bunch of linear functions here and we are looking for a pointwise maximum. So let's say if I take a point right here, then the maximum will be corresponding to this linear function right here. And as a result, considering this for every point, we obtain this convex piecewise linear structure. And this is exactly what we have in the situation when we are trying to maximize what we had there. So we had yi bar transpose times b for I between 1 and n. So we have a finite number of linear functions and we are looking for a pointwise maximum. So, and this was our z of b. So this is the structure that we have here. For a more precise geometrical illustration of our situation, let's consider a case when our change of b, the right hand side, is done in a very particular way. So more specifically, assume that we look at some vector b star for the right hand side which is fixed, and we are trying to obtain a different right hand side by moving from b star along some fixed direction d, and the parameter theta here represents the length of our step size when we move along this direction. Alright, so then we can represent our function z of b as f of theta, a function of just one scalar parameter, which is given by the pointwise maximum here of yi transpose multiplied by b star plus theta d. And in this case, we can plot our function f of theta in 2D, and this is how the plot is going to look like. So you have linear function of theta here for every fixed I, and then we take the pointwise maximum of these linear functions here. So geometrically, yi bar transposed times d will give the slope of the corresponding linear function. So for I equal to 1, this is the slope of this function right here. For I equal to 2, it's the slope of this function, and so on. And now we can plot the function f of theta explicitly, so we can see that you have local linearity for all the thetas that correspond to the non-degenerate primal solutions. And then we have these breakpoints theta 1 and theta 2, where the lines intersect, and we have multiple optimal solutions for the dual problem. Let's say for theta equal to theta 1, we have two optimal dual solutions given by y bar 1 and y bar 2. And in this case, we see that these correspond to these breakpoints, the points of non-differentiability for our function f of theta. So we see that on the plot we have 2 points of this type. Alright, so and for the values of theta for which f is not differentiable, these breakpoints theta 1 and theta 2, the dual problem has multiple optima, and every optimal basic feasible solution for the primal problem is degenerate. Because when we have alternative optima for the dual, this means that we have some zero coefficients in row 0 of the optimal dual tableau, which exactly corresponds to the degeneracy for the corresponding primal solution. Let's go back to the general case of z of b, where we don't restrict ourselves to the change along a line. And in this case, z of b is given by the maximum of y bar I transpose times b for I between 1 and n, where y bar i's are the extreme points of the feasible region of the dual, and this is of course a piecewise linear function. Now, whenever you have local linearity, then the function is of course differentiable because it is linear around the point, right? And this happens when the dual maximum is uniquely achieved at some point y star. And in this case, z of b is given by y star transpose times b. And in this case, the gradient of z of b is given by the optimal dual solution. So now, whenever we don't have differentiability at the point b, we know that every optimal basic feasible solution to the primal problem is degenerate, because if it was not degenerate, then we would have local linearity, and then the gradient would be equal to y, the dual optimal solution. And with respect to the dual, this implies that the dual has alternative optima. So this corresponds to this situation with the breakpoints that we just considered in the illustration. So whenever we do have differentiability, the gradient of z of b is equal to the optimal dual solution for the corresponding value of the right-hand sides. How about the case of non-differentiability? So in this case, actually, it can be shown that the subgradient of z of b is going to be equal to the set of optimal solutions for the dual. So in this case, there will be infinitely many optimal solutions for the dual, and all of these optimal solutions will form the subdifferential of the function z at the point b. And next we are going to discuss what subgradient and subdifferential are. The concept of subgradient essentially extends the definition of the gradient to the convex non-differentiable case. And perhaps it's best illustrated by looking at the first order characterization of a convex function for the differentiable case first. So in this case, of course, the function is differentiable, so we have the gradient. And the first order characterization of the differentiable convex function states that if f of x is differentiable on a non-empty open convex set x, then it will be convex if and only if for any pair of feasible points x and x prime we have this inequality satisfied. So we have f of x is greater than or equal to f of x prime plus the gradient of f in x prime transpose times x minus x prime. And geometrically, this essentially expresses the fact that whenever we have a convex differentiable function, if we draw the tangent line to this function at any point, then our function will be above the tangent line always. And this is an equivalent characterization for differentiable convex functions, so essentially it could be used as a definition of a convex function for the differentiable case. Now, in case of non-differentiabilities, we may not have the tangent line in some cases, right? So let's say if I have a function of this sort, then for the points of non-differentiability, there is no tangent line at this point. But for a certain range of slopes, whenever we draw a line within that range of slopes passing through this point right here, we may have the same property. The whole function will be above this line. And essentially, this is how the concept of subdifferential is defined. So with the gradient, we have a unique vector here for which this property holds, and this unique vector is our gradient. But in case of subgradient, we may have many different lines that have this property here. And for each of these lines, whenever this property holds, the slope of the line will be called the subgradient. So essentially we are going to replace the gradient which doesn't exist anymore with some vector y here, and we'll say that y is subgradient for our function f at the point x prime if this inequality is satisfied for every feasible x. So we obtain the following definition. For f, a convex function defined on a convex set x, let x prime be in the set x. Then we say that a vector y is the subgradient of f at x prime if this inequality is satisfied for every x from the set x. So this is exactly what we just mentioned. Okay, so now we can use the subgradients to characterize the dual optimal solutions in terms of our function z of b. So this theorem provides this characterization. So if we have LP that is to minimize C transposed x subject to ax is equal to b star x greater than or equal to 0, if this LP is feasible and the optimal cost is finite, then a vector y is an optimal solution to the corresponding dual problem if and only if it is a subgradient of the optimal cost function z of b at the point b star. So we saw that in case of differentiability, the gradient of z of b star is actually given by the dual optimal solution y. So in this case, the subgradient is unique. Whenever you have differentiability, the subgradient is unique and it is given by the gradient. However, when we have no differentiability, then in this case we have infinitely many subgradients. And by the way, the set of all the subgradients of f at x is denoted by df of x and is called the subdifferential of f at x. So this set has infinitely many elements and each of these corresponds to the dual optimal solutions. And we can see that this is a one-to-one correspondence. So in case of our optimal value function z of b, we have of course piecewise linearity. And in the case of piecewise linear functions, the subgradient can be described as a gradient of a linear function that lies below f of x and equals to f of x at the point x equal to x prime. And we are talking about a subgradient at the point x prime. So looking at the x prime where the function is actually differentiable because it is locally linear, there is only one slope for which this property is true, right? So the line must be below the function and it must be equal to the function at x prime, and we can see there is only one line like this, right? So at the point of non-differentiability, so if x prime is one of the points where the function is non-differentiable, then there are infinitely many linear functions that have this property. So you see the line is below our f, it is coinciding with f at x prime, so the slope of this line is going to be a subgradient of f at x prime, and there are infinitely many lines with this property. Now that we have a good understanding of the global dependence of the optimal objective value on the right hand side, we can discuss similar properties of the objective as a function of the objective function coefficient c. So if you were to vary the objective function coefficient, then in this case, again, the objective function value may change, right? So, and for the analysis, we essentially look at the dual feasible set. In this case, the dual feasible set will depend on the value of this parameter c, which is the coefficient in the objective, right? So recall that when we are looking at the global dependence on b, then the change in b would modify the feasible region for the primal problem, but the feasible region for the dual wouldn't be affected. So when we are looking at the global dependence on c, it's the opposite. The primal feasible region remains unchanged, but the dual feasible region does change. And then, because the dual feasible region changes, we need to look at the set of c's for which the dual feasible region is actually non-empty. And similarly to the case of changes in B, we can show that this set f prime is actually a convex set. And then if C doesn't belong to f prime, then the dual is infeasible by definition, right? So then this means that the primal will be unbounded, because our assumption was that the primal is feasible. And in case of C belonging to f prime, meaning that the dual is feasible, we will have a lower bound on the primal problem, so we will have a finite optimal cost for both primal and dual. So we conclude that the optimal primal cost is finite if and only if C belongs to this set f prime. So, and this is the case that we are focusing on. So then we define the objective value function as a function from the set f prime to R, given by the minimum of C transposed X, subject to our constraints here. And in this case, we vary C, the vector of the objective function coefficients. And in this case, of course, we have the non-negativity constraints, meaning that our feasible set doesn't contain a line. So this implies that our feasible set has extreme points, and the optimal objective value can be obtained by looking at all the extreme points and picking the one with the smallest objective. So we assume that the extreme points for our primal problem are given by xi bars for I between 1 and n capital. Then in this case we have a piecewise linear concave function, because now we are looking at a bunch of functions for which we take the minimum, right? So if we take a pointwise minimum for a finite set of linear functions, then we'll obtain a concave piecewise linear function. So we look at these pieces that are the lowest in this case. Alright, so in this case we have the concavity instead of convexity. So W of C, the function that represents the value of the objective as a function of the parameter C, is a piecewise linear concave function. So now if we fix C star, the objective function coefficients, so that the optimum is unique and is achieved at some extreme point x bar I, then locally we will have the linear dependence again. So our function W of C is going to be locally linear around the point such that our LP has a unique optimum. However, if we have multiple primal optimal solutions, then we will have non-differentiability for our function W of C. And again, we have a similar situation to what we had with the changes in the right hand side, right? So these points here, they are the points of non-differentiability, so they correspond to multiple optimal solutions for the primal problem, and they correspond to the degeneracy for the dual problem.